Hey everyone, this is Dr. Walker. In this video, I'm going to go over an example from v535, energy stored in a capacitor. This example is actually going to deal with a capacitor with a dielectric. This example, we have a parallel plate capacitor charged with a battery to a charge of Q0, and then the battery is removed. And then we're inserting a dielectric in between the plates of the capacitor. We want to find the energy stored in the system. The system is the capacitor and the dielectric before and after the dielectric is inserted. So how do we find the energy stored in a capacitor? We have three equations right here. And the trick is to know which one to use. So we know, first of all, that when we're inserting the dielectric between the plates, that the capacitance is going to change. We know the new capacitance is kappa times the original capacitance, C0. So we know we want to use an equation that has capacitance. So now I want you to think about, well, which one are we going to use now? The one that has V or the one that has Q? So the trick is to try to use one that has the other variable remaining constant. And this is why in this problem it's significant that the battery is removed, because that's going to tell us what variable is remaining constant. So let's take a look. Let's draw a capacitor and charge it with a battery. When we charge it with a battery, we know that one plate is going to be positive and one plate is going to be negative, and that charge is the Q0 initial. But now we remove the battery. So let's say we just cut off this part of the circuit here. We now have an isolated capacitor. Well, that isolated capacitor, there's nowhere for that charge to go. So once it's removed from the battery, it's going to keep its same charge. So that was the significance of that, to realize that charge is going to remain constant. And that means that we're going to want to use this last equation to find energy. Energy is going to be Q squared over 2C, where we have the initial charge Q0 and the initial capacitance C0. So this is the initial energy. If you wanted to use the second equation here, it would work, but it would be harder because you'd have to figure out how the voltage changes. Because if charge remains constant and capacitance changes, then voltage has to change as well. So that's why it's easier to use an equation that has one variable constant and one variable changing. So we have our expression here for the initial energy. Now we want to find the final energy once we add a dielectric in between the plates. So we have our capacitor with a negative and a positive plate, and we insert a dielectric. What happens to that energy? And what happens may be a little bit counterintuitive. Let's see what happens. The final energy is going to still have the same charge, but it's going to have a new capacitance, 2C, and then we said that C is kappa times C0, so we can plug that in. And then if we compare the new energy to the old energy, we see that they differ by just a factor of kappa, so the new energy is the initial energy over kappa. So what is really significant about this is that the energy, when we add the dielectric, the energy actually decreases, right? Because kappa is greater than 1, so the energy actually decreases. So that may be counterintuitive, but if you think about it, when the dielectric is inserted, it's being pulled in because it's polarizing, and those positive charges are going to be wanting to attract to the negative charge on the plate. The negative charges on here want to attract to the positive. It's polarized. It doesn't want to leave now that it's inserted. So one way to understand that the energy is actually decreasing when we put it in is to think about, well, if we take it out, then the energy is increasing. And the way that we can understand that is because to take it out, we're going to have to do work on this dielectric to take it out since it doesn't want to get out. So we have to do work to take it out. The energy increases when we take it out. That means the energy decreases when we put it in.